Hello guys, how are you today? So today I'm gonna be explaining chapter 5, chemical reactions and stoichiometry, cqds. So we start with section 5.1, question. Convert to the appropriate SI units. So first thing we come upon is the milliliters. When we're dealing with milliliters, that means we are dealing with volume. And what's the SI unit of volume? The SI unit of volume is meter cubed. So to change from milliliters to meter cubed, what do we need to do? We're gonna divide by 10 to the power of 6. And to change from meter cubed to milliliters, we're going to multiply by 10 to the power of 6. That means over here, this should be 25 over 10 to the power of 6. So if I put it on my calculator, 25 over 10 to the power of 6, I get my answer to be 2.5 times 10 to the power of minus 5. Now we move on to part B, which is torr. Whenever we say torr, that means we're talking about pressure, and for pressure, the SI unit of pressure is Pascal. Now, how do we change from torr to Pascal? Very simply, you will multiply by what? By 133.322 Pascal. And when we're going from Pascal to torr, what do? We divide by 133.322. So we're moving from torr to Pascal. That means I need to multiply. It will be now 152 times 133.322 Pascal. This will give me my answer, which is approximately 2,265 Pascal. That's it for part B. Now we'll move on to part C. What does it say in part C? 37 degrees. The SI unit of temperature is what? Is Kelvin. So we need to change from degrees Celsius to Kelvin. When we're moving from degrees Celsius to Kelvin, we add 273.15. And when we are moving from Kelvin to degrees Celsius, we need to subtract 273.15. So from degrees Celsius to Kelvin, we plus 273.15. So 37 plus 273.15, this will give me my answer to be approximately 310.15 Kelvin. Now we finished question 1, we'll move on to question 2. 3 students were asked to weigh 1.20 gram sample using 3 different balances as the first step in an experiment. Each student repeated the weighing 3 times and found the average weight. Their results are shown below. So for trial 1, we have student 1 got an answer, student 2 got a different answer, and student 3 got a different answer as well. For trial 2, all of them different answers, same thing for trial 3, and then they all took the average of the answer. How do you take the average of the answer? So to find the average, you add all of the trials, so trial 1 plus trial 2 plus trial 3, and you will divide it by the number of trials that you executed, so in this case it would be 3 trials. Now, state whether the data of each student is precise or accurate, or whether the errors, if any, are random or systematic in each set of data. Before we proceed, we need to explain what is the difference between precise, accurate, inaccurate, random, and systematic. Now, before we do anything, we need to check if it's precise and accurate, and if it's not precise and inaccurate. First of all, what is the definition of precise? Precise means that the answers are what are close to each other, whereas accurate means that the answers are close, so let me say close to each other for the precise, whereas for accurate, they are close to the original value. So, for example, let us decide whether student 1 has precise and or accurate values. So, first of all, we need to say precise. We look at precise. We have 1.32, 1.15, 1.57. They're all far from each other. So, we say that student 1 has not precise. So, I'm going to write NP, which means not precise. Student 1's results are not precise, as well that if you look at the accuracy, you see that is it closer to the original value? Go back to the original value. The original value is 1.20 grams. So for sure, you have 1.32, 1.15, 1.57. It is what? It is inaccurate. Now, because it's not precise and inaccurate, we can say for sure there is what? There is gonna be some errors. Now let us discuss the errors, whether they are random or systematic errors. If they are random errors, then they go both up and down, like meaning if my value, like the original value that I'm looking at is 1.20, right? I will look, I have this is greater, and this is less than. So it's going like some values are greater than 1.20, some values are less than 1.20. That means for sure this one is random. If it's systematic, that means it's only either going up or only either going down. We'll see an example of this type of error if we move on to the next one, right? So in the next one, I look at it, I see, is this precise or is this accurate, or is this not precise or is this inaccurate? I look, I see that the values are really close to each other, 1.09, 1.10, 1.12. So we can say that they are what? They are precise, P. Now, they are inaccurate because they're very far away from the original value. So I'm going to write here it's inaccurate. Is the error random or systematic? If you look at all of the values, this is less than 1.2, less than 1.2, less than 1.2. That means these are all what? Only less than 1.2. That means this is what? This is a systematic error. Now, last but not least, let us check this value over here. So what do I have? So first of all, these are precise because they're all close to each other, and it is accurate because they're very close to the original value, which is 1.20. They're 1.21, 1.19, 1.22. And here, because it's precise and accurate, two positives, we directly say that it's what? Its errors are minimal. Okay, so that is it for question number 2. We'll move on to question number 3. Give the number of significant figures in each of the following values. We first start. Over here, we have 600, but we have a point. This point, whenever we have a point, any zeros before and any zeros after, unless it's 0.00 something, you don't consider this. This is the only exception, okay? But, for example, in this scenario, I have 6 and then 0, 0, and then a point. If it's 600 only, I would have one significant figure, which is the 6. And these are known as what? These are known as trailing zeros. But, however, I put a point, so now these are no longer trailing zeros. That means I would have 3 significant figures. 400 milliliter, just as we discussed, because there's no point, that means these are tracing or trailing zeros, and I only have one significant figure. Again, what did we say? We said if we have a number and then point something and there's like zeros, right? As long as it's not 0 point whatever. Here in this scenario, it's what? It is 7.0. 7 is a significant figure. Point will make the 0 a significant figure. So that's we have how many significant figures? We have 2 significant figures. Now, I said when we have a point, zeros are considered significant, except the only exception if it's 0.00 something. You don't consider these zeros because they're by themselves. If there's something before it, yes, I would consider it. If there's a non-zero number before it, yes, I would consider it. However, the non-zero numbers are after it, right? So this would be 1, 2, 3, 4, and 5 significant figures. Now, if we ever get an exact value, which is 28 students, can I like say I have 28 and a half students? No, I cannot have half a student. So if you get ever like an exact number, you're describing a physical object, this has infinite number of significant figures. And then this over here has only 1, 2, 3, my pen fell, my bad, has 3 significant figures. We'll move on to question number 4. Complete the table below. Give your answer to the correct number of significant figures. So, the mass of the empty flask is 121.01 grams. The mass of the flask filled with water is 321.0 grams. The density of water is 1 gram per centimeter cubed. They want the volume of the flask. From an equation you're supposed to know, volume is equal to mass over density. So I have the density. I can find the mass of water and then divide it by the density of water. Why? Because I don't have the density of the flask. But however, I do know that water is a liquid, and what do liquids do? They take the shape of its container, meaning it will also take the volume of its container. So the volume of water is equal to the volume of the flask, right? So the mass of water, how do I find it? I take the mass of the flask filled up with water, which is 321.01, and I will subtract from it the mass of the empty flask, which is 121.01 grams. After subtraction, it's supposed to be 200.00 grams. This is the mass of water. So 200.00 grams divided by the density of water, which is 1.00. I'm gonna get it to be 200 milliliters. Why didn't I put the 0.00? Because when we're doing addition and subtraction, you do based on the least number of significant figures. Same exact thing when it comes to division and multiplication. You always get your answer to the least number of significant figures. So between 5 and 3, 3 is the least, so our answer should have 3 significant figures, which is how much? Which is 200 milliliters. So this volume of water is gonna be what? It's also gonna be the volume of the flask. Perfect. Now, they removed the water. They used the same flask with the same mass of the beginning. And then they told us that the mass of the flask filled up with CO2. Okay, so again, we have the my bad. The mass of the flask filled up with CO2 gas with the mass of the empty flask, right? So what will we be able to find? We'll be able to find the mass of CO2 in the flask. So it will be 123.2 minus 121.01. You'll get your answer to be 0.2 minus 121.01. You will get your answer to be 2.19. However, you need to take it to the smaller number of decimal places, which is 1, right? So it's gonna be 2.2 after rounding. That means the mass of CO2 in the flask is 2.2 grams. Now, how do you find the number of moles of CO2? It's mass over molar mass. So 2.2 over 44. So that's gonna be 0.050 mole. Now, what did they give us? We have the number of moles, and we know N equal this. We know that R is equal to what is equal to 0.082. They gave us the temperature, which is 300 Kelvin, and we have the volume of what? We have the volume of the flask. Since CO2 is also what is also a gas, that means it's gonna take what? It's gonna take the volume of the flask. That means basically the volume of the flask, which is 200 milliliters, is also gonna be the volume of CO2. Now you need to change everything into their SI unit. Everything is changed into their SI unit except the volume. So you need to change it from milliliters into meter cubed, right? Or no, not meter cubed, into liters. So you need to change it from milliliters into liters. How do you change that? You change that by multiplying by 10 to the power of minus 3. Okay, so now we can apply the rule PV equals nRT. So pressure, which is what we need to find, is equal to nRT over V. So 0.050 times 0.082 times 300 over 200 times 10 to the power of minus 3. Put it on the calculator and you will get 6.2 atmospheres. Why did I say 6.2 atmospheres? Because my smallest significant number is what is 2. Because look, here this is 3 significant figures. This is, I forgot to put the point. My bad. Don't forget to put the point. This is 3 significant figures as well. This is 2 significant figures. This is also 2 significant figures. So you take the smallest one, which is 2 significant figures, and you get your answer to be what? To be 6.2 atmospheres. We finished 5.1. We'll move on to 5.2. How many molecules of water are there in 18 grams of water? Do you remember the triangles we took in grade 9, right? Which is number of moles is mass over molar mass. Number of moles is the given volume over either decimeter cubed or either STP or RTP. So I'm gonna call this STP, or RTP. And then the number of moles is also equal to what? Is equal to the number of molecules over what? Over Avogadro's number. AN means Avogadro's number, AN. So what are they looking for? They're looking for the molecules of water. So directly you go to the equation with molecules. That means the molecules is equal to Avogadro's number times the number of moles, N. They also gave us the mass of water, and we can find the molar mass of water. That means N is equal to mass over molar mass. That means the molecules is now equal to Avogadro's number times mass over molar mass. Avogadro's number, you guys are supposed to have it memorized. It's 6.02 times 10 to the power of 23 times the mass, which is 18 grams of water, over the molar mass of water, which is also 18 grams, will give me 6.02 times 10 to the 23. So we will have 6.02 times 10 to the 23 what? Molecules. That's it for question number 5. We move on to question number 6. Find the number of moles of chloride ions in a 234 gram sample of sodium chloride. Very important, they want the number of moles of chloride ions. First of all, what do? We take our thing, NaCl, and we split it into its ions. Na plus, Cl minus. The ratio is what? The ratio is 1 to 1. Very, very important to know. Now what do? We find the number of moles of NaCl. Number of moles of NaCl is equal to the mass over the molar mass. So the mass of NaCl is how much? It's given to us as 234 over the molar mass of NaCl. Na is 23, Cl is 35.5, so that's 58.5. So the number of moles of NaCl is 234 over 58.5, which is what? Oops, my pen flew. Which is what? Which is 4. So the number of moles of NaCl is what? Is 4. Now, of course, since it's a 1-to-1 ratio, what does this mean? This means 1 NaCl will give me 4 moles. 1 Na plus will give me 4 moles. 1 Cl minus will give me what? Will give me 4 moles. Okay, that's it for question number 6. We'll move on to question number 7. An 18-gram sample of compound X is composed of 0.100 mole of the compound. Find the molar mass of compound X. What's this question? Mass over molar mass equal number of mole. 18 over molar mass equals 0.100. Molar mass equal 18 over 0.100. What does this mean? This means the molar mass, you need to write it, of course, to the correct significant figures. Oh, my bad. I'll go up to question 6 and write it to the correct significant figures. The molar mass of compound X is what? Molar mass of compound X is gonna be what? You see, what's the least significant figures? 3, so it should be 1.80 times 10 to the power of 2 grams. Now we go back up to question 6. Here we got the answer to be 4 moles. But if you look, you see everywhere, the least number of significant figures is 3. So it's not 4 moles, it's 4.00 moles. We'll move on to question number 8. What does it say? Find the percent composition by mass of each element in each of the following compounds. First of all, you need the percent composition of hydrogen in H2SO4, sulfur in H2SO4, and oxygen in H2SO4. We first start by taking how many hydrogens, how many sulfur, how many oxygen do I have? 2 hydrogen, 1 sulfur, 4 oxygen. Now I multiply each of these by what? By their molar mass given to us. So times 1.01 times 32.10 and times 16.00. Now, of course, don't forget to add them all to get what? To get the total mass. So 2 times 1.01 plus 1 times 32.10 plus 4 times 16. That's gonna give me a total mass of what? A total mass of 98.12. Now, how do I find the percentage mass? It's gonna be mass over total mass times 100. So 2.02 over 98.12 times 100, right? 32.10 over 98.12 times 100, and then 4 times 16, that's gonna be 64 over 98.12 times 100. Okay, so 2.02 over 98.12 times 100 will give me my answer to be what? To be 2 0.06%. How did I know what significant figure do I take it to? I check what's the least number of significant figures. It's 3, because here, 3. Perfect. That means all of my answers should be to 3 significant figures. Actually, no. It's not necessary all of them to be to 3 significant figures. Sorry, my bad. Because of hydrogen, it has 1.01, right? Then when you're doing the division, you take 2.02 over 98.12, right? Now, which has the least significant figures? 2.02, which is 3, so you'll base it off of this. Now, when you move on to sulfur, you will see that both numerator and denominator have the same number of significant figures. That means my answer should be to 4 significant figures, right? So, 32.10 over 98.12 times 100, right? This will give me my answer to be what? My answer should be 32.72%. Now, last but not least, for oxygen, it's gonna be what? It's gonna be 64.00. Please don't forget significant figures. I'm doing that a lot. It will cost me, and if you do it in the exam, it will cost you a lot of marks, right? 64.00 over 98.12 times 100. What's the smallest significant figure? It's 4. That means my final answer is gonna be 65.23%. Okay, so that's it for the first part. For part B, what does it say? For KHCO3, again, I prefer to do a table for all of them. We have K, we have H, we have C, and we have O3. We first of all start by writing like the ratio. We have 1K, 1H, 1C, and 3 oxygen. Now multiply it by what? Multiply it by their given mass, right? So it's gonna be 1.01 over here for hydrogen. For carbon, it's gonna be 12.00. For oxygen, it's gonna be 16.00, and for potassium, it's gonna be 39.10. I think I can't move my screen, but I'm getting the answer, so 39.1 from the answer key, okay? So now what do? We multiply them all. We get, first of all, the total mass, okay? So it's gonna be 1 times 39.1, okay? Plus 1 times 1.01, plus 1 times 12, plus 3 times 16. This will give me my answer, which is what? Which is 100.11 grams. I don't know if it's visible. Let me make it more visible. 100.11 grams. Perfect. Now, how do I find the percentage? I'm going to take the mass of this, 39.1 over 100.11. For sure, 3 has, I think this is 39.10. I'm not sure because I cannot see. But 39.10 over 100.11 times 100. Which one has the smaller number of significant figures? Definitely 39.10. So it should be to 4 significant figures. So 39.06%. Now, for hydrogen, it's gonna be 1.01 over 100.11 times 100, right? What are you gonna do now? You're gonna multiply. You're gonna take the significant figures, right? The least significant figures, which is 1.3, so it's gonna be 1.01%. Now, for C, carbon, it's gonna be 12.00 over 100.11 times 100. So 12.00 is only 4 significant figures, so your answer will be 11.99%. And then last but not least, oxygen, which is 3 times 16, what's basically 3 times 16.00 over 100.11. Of course, since it's to 4 significant figures, our answer should be to 4 significant figures. So it's gonna be whatever the answer is, okay, times 100. So all of this times 100, which will give me an answer of 47.95%. Now, last but not least, we have MgCl2, right? We draw the table. We have Mg, we have Cl2, we have total mass here, we have the ratio, so 1 times Mg, which is 24.30, and then 2 times Cl, how much was Cl given to us? Cl was given to us as 35.5. So the total mass is 24.30 plus 2 times 35.5, which is what? Which is 95.3 grams, the total mass. Now what do? We do the mass divided by the molar mass times 100 to get the percentage. So for magnesium, it's going to be 25.5%. And then for Cl2, it's going to be what? It's going to be 2 times 35.5 over 95.3 times 100. So if I put it on my calculator, I'm supposed to get an answer of, oh, I forgot to put it to 4 significant figures over here. No, it should be 3. Because the smallest significant figures is 3, okay? And then here it's gonna give me an answer of 74.5%. Perfect. So that's it for question number 8. We'll move on to question number 9. A sample of hydrated CuSO4 with a mass of 25 grams was heated until all the water was removed. The sample was then weighed and found to have a mass of 16 grams. What's the formula of the hydrate? What do they mean by formula of the hydrate? Meaning they want to find, it's going to be CuSO4 X, let me say XCuSO4 YH2O. It's going to be something like this. They want us to find the formula of the hydrate, which is this, okay? First off, we start that the original mass was how much? Was 25 grams. 25 grams is equal to what? Is equal to the mass of CuSO4 plus the mass of water. They told us that after it was heated, okay, after all of the water was gone, the mass of the remaining, which is CuSO4, is 16 grams. That means how much would the mass of water be? The mass of water would be 9 grams. Now what do? 9 grams divided by the molar mass, 18, will give me the number of moles, which is what? Which is 0.5 mole. And then the mass over the molar mass will give me the number of moles, which is 0.1 mole. Now how do I find this? I'm going to make it a ratio, right? So I'm going to do the number of moles of CuSO4 over number of moles of H2O. And it's going to give me an answer of 1 over 5. That means 1 CuSO4, 5 H2O. So this is my answer. Just like that, we finished 5.2. We'll move on now to 5.3. Chemical equations. Balance the following equations. First of all, we start here. Let me just write it. H2 plus N2 gives me NH3. I write under my hydrogen and my nitrogen. How many hydrogen do I have? I have 2. How many nitrogen do I have? I have 2. Here, my hydrogen, my nitrogen. I have 3 hydrogen, 1 nitrogen. What happens if I put a 2 over here? It becomes 2 nitrogen and 6 hydrogen. That means the only thing I need to change now is this. So I can put a 3 over here and I will have what? I will have 6 hydrogen. So 6 hydrogen, 6 hydrogen, 2 nitrogen, 2 nitrogen. It's balanced. So this is my balanced equation. We're going to do the same exact thing for C4H10 plus O2 gives me CO2 plus H2O. I start. How many elements do I have? I have 3 elements. Carbon, hydrogen, oxygen. Carbon, I have 4 carbon here, 10 hydrogen here, 2 oxygen. Here, my carbon, my hydrogen, my oxygen. My carbon, I only have 1 carbon. My hydrogen, I have 2 hydrogen. Whereas my oxygen, I have 2, 1. Why do I do 2, 1? Because I have it split into here and here. I have 2 oxygen and CO2 and 1 oxygen and H2O. So it's important to split it up. Okay? Now, because oxygen is split up, we will leave it for the last thing. And we're left with what? We're left with H10, H2, C4, C1. Now let me try changing here. If I put a 4 over here, my carbon will become 4. Okay, so now 4 carbons on both sides. But what happens to my oxygen here? It becomes 4 times 2, which is what? Which is 8. Now, what if I put a 5 over here? If I put a 5 over here, this will be 2 times 5, which is 10. And this would be 1 times 5, which is 5. So in total, this is now what? This is now 13. So 2, 13, that doesn't work out. So I'll just need to multiply by 13 over 2. However, in exams, they usually don't like to see 13 over 2. So what can we do in this scenario? They don't like to see over 2, so how can we get rid of it? We can multiply the whole thing by 2. Once I do that, I will get 2C4H10 plus 13O2 will give me 8CO2 plus 10H2O. Okay, now we'll move on to the next one, which is SO3 plus H2O gives me H2SO4. What elements do I have? I have sulfur, I have oxygen, I have hydrogen. Sulfur, I have 1 over here. Oxygen, I have 3, 1. Hydrogen, I have 2. Sulfur, oxygen, hydrogen. Sulfur, I have 1. Oxygen, I have 4. And hydrogen, I have 2. I don't think this needs balancing. 1, 1, 4, 4, 2, 2. There's no need for balancing. It's already balanced. Perfect. Question number 11. When an aqueous solution of hydrochloric acid, HCl, is added to a solid sample of calcium carbonate, say CO3, the carbon dioxide gas, CO2, water, H2, and aqueous solution of calcium chloride are produced. They want the chemical equation for the reaction described above. So, I start with Ca, CO3, okay? It's added, like, it's first of all what? A solid, okay? It's a solid sample. We add to it what? We add to it HCl, which is what? Which is aqueous. They told us it's aqueous. And what will it give us? I'm going to put it down because it's not going to fit. I know it's not going to fit. It's going to give us, first of all, CO2 gas, water, which is a liquid, and aqueous solution of CaCl2. Perfect. Now, is this balanced? No, it's not balanced. How do I balance it? I have 2 hydrogen. I just put the 2 over here. And just like that, my equation is balanced. Now they want the net ionic equation of the reaction. Now what does this mean, net ionic equation? Whenever they say net ionic equation, you see. I will look at my product. I will see anything that's aqueous. If I have anything aqueous, I will ignore every single thing there, right? What does this mean? This means I will ignore Ca and I will ignore Cl2, right? That means I ignore Ca and I ignore Cl. So now I'm left with what? I'm left with CO3, 2 minus. Actually, no, you can't turn it into ions, my bad. This is why you don't change it. CaCO3 stays because you cannot turn it into its ion, so it will stay. CaCO3 solid because it's a solid plus. I got rid of the Cl. What am I left with? I'm left with 2H plus aqueous, right? What does this give me? This will give me, you ignore anything aqueous and you write all the remaining products. So CO2 gas plus H2O liquid, okay? So that's it for question number 11. We will move on to section 5.4, question number 12. We'll move on to question number 12. A sample of 3.20 kg of iron oxide is heated with excess carbon to extract iron as whatever the following. Calculate the mass of the theoretical yield. How do we calculate the mass of the theoretical yield? First of all, we need to identify the limiting reagent ratio, the LRR as I call it, the limiting reagent ratio. After that, okay, we need to find what we need to do stoichiometry. Okay, after doing stoichiometry, we will get what? We will get our answer. So first of all, let us find the limiting reagent ratio. So iron 3 oxide with excess carbon, that means this is an excess, this is our limiting reagent, right? Now, what is the molar mass of iron 3 oxide? In order to find that, we see it's Fe2O3, so it's going to be 56 times 2 plus 16 times 3, so that's going to be 160. Now you would take the given mass, which is 3,200 grams over 160, which will give me the number of moles to be what? To be 20. Perfect. So that means if 2 moles became 20 moles, how much will 4 moles become? Why did I choose Fe? Because I know CO2 is definitely what? It's definitely a gas and it's not what we're looking for, actually, if you continue reading, they'll tell you it's iron that's produced. So they're dealing with iron, okay? So if 2 becomes 20, then 4 will become 40. So how much will be the theoretical mass of iron? It will be the number of moles times the molar mass, which is what? Which is 2240 grams, which if you change it into kg is 2.24 kg. Now I have what? I have my theoretical yield. Now they told us that the actual mass or the actual yield produced is 1.68. Find the percentage yield. Is going to be the actual over the theoretical times 100, right? So 1.68 over 2.24 times 100, it will give me 75%. We'll move on to question number 13. A sample of 4 decimeter cubed of nitrogen gas N2 reacts with 6 decimeter cubed of hydrogen gas H2 under the same conditions of temperature and pressure to produce ammonia gas NH3. So let us first of all draw or write the equation or the equation. They said nitrogen gas, which is N2, reacts with hydrogen gas H2 to produce NH3. Unbalanced, how do you balance it? 2 here, 3 here. Now what did they say? They said 4 decimeter cubed of nitrogen gas, 6 decimeter cubed of hydrogen gas. Okay, now they said how much ammonia in decimeter cubed is produced if the reaction goes to complete. So first thing we need to do in this scenario is we need to find the limiting reagent ratios. Okay, let us do the limiting reagent ratios for each of them. We'll take the volume divided by the coefficient, right? So for N2 it's 4 over 1. For H2 it's 6 over 3, so 4 and 2. For sure 4 is greater than 2. That means my limiting reagent is what? Is H2. What does this mean? This means my whole equation revolves around H2, right? That means if 3H2 became 6 decimeter cubed, that means 2H2 is gonna be what? It's gonna become 2 decimeter cubed. Perfect. Now, if the percentage yield was 75%, how much ammonia gas was actually produced? That means it's gonna be X, which is the actual produced, over 4, which is the theoretical produced, is equal to 75%. That means X is equal to 4 times 75%. So X is equal to what? X is equal to 3 decimeter cubed. Don't forget to put it to the correct significant figure, so 3.0 decimeter cubed. We'll move on to question number 14. A sample of 10 centimeter cubed of a gaseous hydrocarbon CxHy reacts completely with oxygen gas under the same conditions of temperature and pressure and forms 40 centimeter cubed of carbon dioxide and 50 centimeter cubed of water vapor. Find the molecular formula of the gaseous hydrocarbon CxHy. So basically, they're telling us to write whatever is happening. CxHy, in addition to oxygen, we don't know how much oxygen, is gonna give us what? Is gonna give me X CO2 plus H2O, right? Actually, without the X, we don't need the X. Let us balance the equation now, okay? First step, the most important step to do is to balance the equation. So I have XC's, right? That means, let me do it in this way. Carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen. I have X carbons over here, Y hydrogens, and 2 oxygens. I have 1 carbon, 2 hydrogen, and 2 and 1 oxygen. Okay, so how do I get 1 to become X? Very simply, I multiply it by X. If I did multiply it by X, what will happen? I will also multiply this by X. So now this is what? This is X. How do I get 2 to become Y? Very simply, I multiply it by what? By Y over 2. So now this is Y over here, right? So what do I need to do here? I need to multiply it by Y over 2. So now I have Y here. And then this would be what? This would be Y over 2. Okay, now, how do I make this oxygen work based on here? Very simply, I will take whatever number I have here, which is 2, and I will divide all of this by what? By 2. When I do divide by 2, I will get left with what? I'll be left with X and Y over 4. So now what do I put over here? Over here I put x plus y over 4. Now this is my final balanced equation. Now what can I start doing? I can start by putting under each one of them their volume. So this is 10 centimeter cubed. I don't know for oxygen the volume. For CO2 it is 40 centimeter cubed, and for H2O it's 50 centimeter cubed. Since they're all in centimeter cubed, I can divide by the smallest number, which is 10. If I do, I will get what? A ratio, which is what? Which is 1, 4, 5. Now, they told us that all gases are under the same condition of temperature and pressure. Because of this, because they're under the same condition of temperature and pressure, what's the equation? PV equals nRT. That means PV over nRT. Okay, so P1V1 over N1 RT1 is equal to P2V2 over N2 RT2. They told us that it's the same pressure, so you can erase this because they will cancel out. The same temperature, so you will erase this and it will cancel out. R is always the same, so now we're left with V1 over N1 is equal to V2 over what? Over N2. So what does this mean now? This means I already used my volume, and what's left for me to use is the moles. So I can say that this is 1 mole, this is 4 moles, and this is what? This is 5 moles. Now, what do I have? I have that x is the number of moles and 4 is the number of moles. That means x is equal to 4. Y over 2 is the number of moles, and 5 is the number of moles. So that means y is equal to 10. Okay? Okay, so what does this mean? My equation is going to be C4H10. Perfect. We'll move on to question number 15. Propane, C3H8, undergoes complete combustion when it reacts with excess oxygen to produce carbon dioxide and water. Calculate the volume of carbon dioxide gas produced at RTP if 2.20 grams of propane reacts with excess oxygen. So, propane will produce what? First of all, let's write the equation. C3H8, okay, undergoes combustion with excess oxygen, so plus O2 will give me what? Oh, why am I writing the equation? They gave me the equation. Okay, my bad, guys. They already gave us the equation. C3H8 plus 5O2 will give me 3CO2 plus 4H2O. What did they say? They said they want the volume of carbon dioxide gas produced at RTP. So what will we need to do in this scenario? We need to find out which one is the limiting from the given excess oxygen. This is the excess and this is my limiting, right? So they said, what's the volume of carbon dioxide produced if 2.2 grams of propane reacts? So it's going to be, first of all, you need to find the number of moles of propane. So number of moles of C3H8 is equal to 2.20 over the molar mass, which is 12 times 3 plus 8, right? So 2.2 over 12 times 3 plus 8. This will give me my number of moles to be 0.05 moles, okay? So now, if 1 gave me 0.05 moles, how much will 3 give me? You need to do cross multiplication now. It's gonna give me 0.15 moles, right? Now, whenever they say RTP, it's 24. When they say STP, it's 22.4. So I'll take my number of moles and I will multiply it by the RTP volume, which is 24, and it will give me my answer to be 3.6 decimeter cubed. We'll move on to question number 16. Consider the following reactions. CS2 liquid plus O2 gas gives me what? Gives me CO2 gas plus SO2 liquid. Write the balanced equation. So let us see. How can we balance this? I have 2s over here, 1s over here, so I can put a 2 over here. Actually, let me do like how I was doing before. CSO. Then here, CSO. See here, I have 1 carbon, 2 sulfur, 2 oxygen. Here I have 1 carbon, 1 sulfur, 2 oxygen, and 2 oxygen. So oxygen, I leave it for last. It will balance out itself. How do I make this 1 sulfur go to 2? I will multiply it by 2. So now it's 2 sulfur, okay? And what happens to this oxygen? It will be multiplied by 2, so it's now 4. 4 times 2 is how much? Is 6. So how do I make this into 6? I'll multiply it by 3. So this is my balanced equation. Now, what do they want? If 48 decimeter cubed of O2 is allowed to react with excess amount of CS2, so this is the excess and this is my limiting, okay? Determine the volume of SO2 produced at RT. Okay, now here seriously we can just do like cross multiplication. If 3 gives me 48, how much will 2 give me? You can just do 48 times 2 over 3. It will give you the answer, which is what? Which is 32 decimeter cubed. And just like that, we finished 5.4. We'll move on to 5.5. Solution and concentration. Write the steps needed to separate a mixture of alcohol, boiling point of 78 degrees Celsius, sand, and water into its components. Now, before you think, is sand soluble in alcohol or in water? No. So directly, the first step, what do you need to remove? You need to remove an insoluble solid. How do you remove an insoluble solid? By filtration. After that, you have two miscible, which means they mix in each other, liquids, okay, together. How do you get rid of them? You get rid of them by fractional distillation, right? So this is, first of all, we are writing the experiments. For the filtration, what are we gonna do? We need to set up a filtration, right? We need to set up a filtration, meaning we need the filter paper, we need the funnel, we need the stand, we need the filter, basically everything. Then what do? We pour the mixture and the sand will remain as what? The sand will remain as the residue. Now you're left with a solution of water and alcohol, which are two miscible liquids. That means we separate it in fractional distillation, right? So we need to prepare the system. We first of all need to put water and ethanol, and then we will heat it, and we put a fractionating column, and then a condenser, and then after many tries, we will finally separate water and ethanol, but it's not gonna be purely separated. This is something very important to know. We move on to question number 18. Consider the paper chromatogram shown in the figure below. Okay? Okay, so question number 18. Consider the paper chromatogram shown in the figure below. Calculate the RF values of compounds A, B, and C. How do we calculate the RF values? First of all, we need to take the baseline value, which is over here, right? Which I believe is 2, 1. Then I need to go to the solvent front, which I believe is all the way up here, 11. Then I take the difference, and I will get this to be 10. Now, whatever answer I get, okay, I'm gonna divide it by what? I'm gonna divide it by 10, which is the difference between the solvent front and the baseline. Okay, so for A, you always take it with respect to the baseline. So this is gonna be what? It's gonna be 3 minus 1, which is 2, right? That means the RF of A is what? It is 2 over 10, which is what? Which is 0.2. The RF of B is 6 minus 1, which is 5, so 5 over 10, which is what? Which is 0.5. And then C is 7, so RF of C equals 7 over 10, which is what? Which is 0.7. So we found the RF values of A, of B, and of C. They said the solvent used in the above PC is ethanol. List compounds A through C in increasing order of relative solubility in ethanol. So basically, you'll just go back to the chromatogram paper, and we will see the shorter the distance, that means the less soluble. The greater the distance, that means the more soluble. Or basically, think of it in this way. The more soluble a substance is in the solvent, right? So for example, substance C is very soluble in ethanol. That's why it takes a longer distance for it to separate from ethanol. So that's why A has a smaller solubility than B, has a smaller solubility than C. So C has the greatest solubility, A has the least solubility in ethanol. So the more soluble something is in the solvent, the greater time or the greater distance it takes in order for it to separate. Okay, so that's it for part B. Part C, which of the above compounds is most polar? Okay, basically speaking, whenever we say polar, we directly think of what? We directly think of water. Whenever we say polar in chromatography, we directly think of water. Then we think the water trapped between the cellulose of the molecules of the paper are the stationary phase. Right? This is very important to mention. The water trapped between the cellulose molecules of the paper are the stationary phase. Now, of course, water is more polar than ethanol. Very important information. Water is more polar than ethanol. Right? So, if something is soluble in water, it's gonna be less soluble in ethanol. What does this mean? This means our answer should be A. Why? The more soluble it is in water, let's say is very, very soluble in water, the less soluble it's gonna be in ethanol. Why? Because water is more polar than ethanol, so the water will dissolve A more strongly than ethanol will dissolve A. So thus we can say what? We can say that the polar compound must be A. When they ask why, you say because it traveled the least distance and it has a higher solubility in the more polar water than in ethanol. We move on to question number 19. What does it say in question number 19? A sample containing a mixture of analgesics is analyzed using thin layer chromatography. Identification of the mixture's components involves calculating each component's RF. Define RF. How can you define RF in the exam? RF is the distance traveled by solute over the distance traveled by solvent. Okay, so in the exam, if they asked you to define RF, it's the distance traveled by the solute over the distance traveled by solvent. Part 2. Identify the mobile phase and the stationary phase in thin layer chromatography. Okay, so how did they say this in the answer key? In the answer key, they said that the stationary phase is a thin layer of a fine solid. So thin layer of a fine solid. You can specify to be more specific, usually silica, which is SiO2 or alumina, Al2O3, coated on a glass slide or metal plate. So if they ask you what's a stationary phase, it's a thin layer of a fine solid coated on a glass slide or a metal plate. Okay? Then, if they asked us, what is the mobile phase? Okay, the mobile phase refers to the solvent or the mixture of solvents. So solvent or mixture of solvents used to carry the sample components along the stationary phase. So along the stationary phase. So in the exam, if they asked you describe mobile phase, you'd say it's the solvent used to carry the sample components along the stationary phase. That's it for part A. We'll move on to part B of question 19. What does it say? It says the TLC chromatogram of the given mixture is shown in the diagram below. The mixture to be analyzed was placed at point D. Acetaminophen or acetaminophen was placed at point A. Caffeine was placed at point B. Aspirin was placed at point C. Now, they told us label parts 1, 2, 4. 1 is known as the solvent front. It's basically the maximum point the solvent reaches. 2 is the stationary phase because it's what? It's a thin layer of silica on glass. So it's the stationary phase. 3 is the baseline, which is the starting point of where you put the solvent. So the baseline. And then 4 is what? 4 is the solvent itself, or in other terms, the mobile phase. Okay? So that's it for part 1. We'll move on to part 2. What does it say? Okay, so part 2. Calculate the RF for each analgesic. So how do we calculate the RF? First of all, we need to see the distance traveled by the solvent, okay? So if this is 2 centimeter and this total distance was 10 centimeter, then what was the distance from the baseline to the solvent front, or the distance traveled by the solvent, which is what? Which will be 8.0 centimeters, right? Now that we have this information, we can find the RF value for each one. We know the distance traveled for each of them. We'll just now divide it by the distance traveled by the solvent, which is 8.0 centimeter, 8.0 centimeter, 8.0 centimeter. When you put it on the calculator, here you're going to get 0.063, 0.044, and 0.30. Okay, that is for part II. Part III, knowing that silica gel is polar, okay, arrange the 3 analgesics in order of increasing polarity. Okay, so you take their RF values. This is 0.30, this is 0.044, and this is 0.063. Right? The more polar something is, the less distance it travels. So this is something important to know. More polar, less distance traveled. Okay? So in this scenario, aspirin would be the least polar. Then comes acetaminophen, which will be in between. And the most polar out of all of them would be caffeine, which moved the smallest distance out of all of them. So the more polar something is, the less distance it travels. We'll move on to part IV. They said explain your answer to part BIII in terms of interaction and polarity. So now they're telling us why, if something is more polar, it will travel a less distance. Well, you have to think about it as interaction. The more polar something is, the more it reacts with the polar sheet behind it, the polar silica gel. Let me say, the more it reacts with the polar silica gel. And the more it reacts with the polar silica gel, the less distance it travels. Okay, so this is very, very important. Okay, in the exam, if it might come to you to arrange based on order of increasing polarity, remember, the more polar, the less distance it travels. Is why? Because the more polar it is, the more it reacts with the polar silica gel, and the less distance it will travel. Okay, now we'll move on to part V. It says, what type of chromatography is TLC? TLC is an adsorption chromatography. Now, why exactly is it adsorption? First of all, what does adsorption mean? Adsorption is the attraction and sticking of molecules to a surface. So attraction and sticking of molecules to a surface. Now, why is chromatography in TLC adsorption? Because silica gel is polar. What were we talking about? We were talking about the more polar something is, the more it gets attracted to the silica gel being polar, right? So the more it sticks to a surface. So now we can say, due to silica gel being polar, okay, attraction and sticking of molecules to a surface increases, right? So then we can say what? We can say that the type of chromatography in TLC is what is adsorption. Part VI, identify the components of the mixture placed at point D. So let's go to point D. What do we have in point D? Point D, we have a little bit of component A and a little bit of component C. So what can we say? We can say that, okay, B was the least traveled distance, so B is caffeine, okay? And then the in-between distance is acetaminophen, and then the greatest traveled distance was aspirin. So what can we say now? We can say, based on what we identified, that the two components found in D is what is acetaminophen, in addition to what? In addition to aspirin. Why? Because D shares the same distance as A and C, and A was acetaminophen, and C was what was aspirin. Okay, so that was it for question number 19. We'll move on to question number 20. What mass of H2SO4 is needed to prepare 500 milliliters of 2 molarity solution? Now, very important, mass, okay, prepare 500 milliliter 2 molarity solution. What can I think of when I look at this? I need to find something that will relate mass to concentration and molarity. Then I think directly that number of moles is equal to mass over molar mass, and number of moles is equal to concentration times volume. So what does this mean? This means my mass over my molar mass is equal to concentration times volume. That means my mass is concentration times volume times molar mass. So of course you need to change everything to their SI units. So this will be 0.5 liter, 2.0 molarity, and then the molar mass of H2SO4, it's gonna be 2 plus it's gonna be 98, so it's gonna be 2 times 0.5 times 98, which will give me an answer of what? Which will give me an answer of 98 grams. That means the mass of H2SO4 needed is 98 grams. I'll move on to part B. What does it say in part B? In part B, 25 milliliter of a 0.40 molarity salt solution were evaporated to dryness. 1.11 gram of the salt was left over as a residue. Calculate the molar mass of the salt. So how do we find the molar mass of the salt? We know, how do we relate concentration and volume to the mass and the molar mass? Mass over molar mass equal number of moles. Number of moles equal concentration times volume. That means mass over molar mass is equal to concentration times volume. Now I need my subject to be the molar mass, so I could move it here, right? So now I would have mass is equal to concentration times volume times molar mass, and then I could move these, and now I would have molar mass is equal to the mass over the concentration times the volume. So the mass, which is 1.11 gram, over 25 divided by 1000 liters, multiplied by what? Multiplied by 0.40 molarity. So 1.11 over 25 divided by 1000 times 0.40. This will give me my molar mass M to be what? To be 111 grams per mole. So that's it for this question. We'll move on to the next question. What volume? So they're looking for the volume of a 2 molarity, this concentration HCl solution contains 3.65 gram of solute. So very simply, they're telling us again, number of moles equals mass over molar mass, number of moles equals concentration times volume, mass over molar mass equals concentration times volume. We need volume to be the subject of the equation. That means mass over molar mass times concentration is going to give me the volume. So it's going to be the mass, which is 3.65, over the molar mass of HCl, which is 36.5, times 2. This should give me the volume in the SI unit. So 3.65 over 36.5 times 2. This should give me the volume, which is what? Which is 0.05 liters. Change it if you want into milliliters. So times 1000 will give me 50 milliliters. That's it for question number 20. We'll move on to question number 21. A 0.150 gram sample of solid lead 2 nitrate is added to 125 milliliter of 0.100. Okay, first of all, this is mass. Is added to 125 milliliter volume of concentration sodium chloride solution. Assume no change in volume of the solution. Okay, The chemical reaction that takes place is represented by the following equation. They told us, state what will be observed when the two solutions are mixed. Based on the equation they gave us, we will have a solid in addition to something aqueous. We don't observe anything aqueous. However, we observe a solid, and PbCl2 is what is a white solid or a white precipitate forms. Write the net ionic equation of the reaction that took place. What did we say? Whenever we're writing the net ionic equation, we don't take into consideration the aqueous. That means we're not going to take into consideration the Na, and we're not going to take into consideration the NO3 too. Okay? Now, this only works because they're both aqueous, but if they were solid liquid gas, not aqueous, you could not separate them. You could not separate them into their ions like that, okay? So the net ionic equation of the reaction that took place, it will be Pb2 plus in addition to 2Cl minus would give me PbCl2 solid. And don't forget that this is aqueous, and this is also what? This is also aqueous. Now what did they say? They said calculate the number of moles of each reactant. Very nice, very simple. First of all, we find the number of moles of this. They gave us the mass, so 0.150 over lead nitrate. What is the molar mass of lead nitrate? The molar mass of lead nitrate is 331 grams. So from this, we'll find the number of moles of lead nitrate, which is going to be 4.53 times 10 to the power of minus 4 moles, right? Now, very important is that we separate into their ions. We have Pb2 plus and NO3 minus. As you can see, they don't balance each other out because I have 2 positive, 1 negative. So I'll put a 2 over here and now it's balanced. So if I'm looking for the number of moles of each reactant for, actually, I'm not going to get into that detail yet because they're going to ask about it in part D. So please ignore that, okay? I think they mean part E because this is D. In part E, they're asking about it. So please ignore whatever I just said, okay? So how do you find the mass of PbNO3? Sorry, the number of moles of PbNO3, mass over molar mass. Now for NaCl aqueous, how do you find the number of moles? It's going to be the concentration, which is 125 times 10 to the power of minus 3 because you need to change it to liters, right? Multiplied by what? Multiplied by the concentration, which is 0.1, and it will give what? It will give 1.25 times 10 to the power of minus 2 moles. Very important to keep in mind. Now part D. Identify the limiting reactant. Show calculations to support your identification. How do you find the limiting reactant? You need to find the limiting reactant ratio. So you take the number of moles of PbNO3, right? And you divide it by the coefficient. So 4.53 times 10 to the power of minus 4 divided by 1. And then this is for PbNO3. And then for NaCl, it's going to be 1.25 times 10 to the power of minus 2 divided by what? Divided by 2. Now, I think in the answer key, they solved it wrong, okay? Because they put the number of moles of NaCl to be 1.25 times 10 to the power of minus 4. No, it's 1.25 times 10 to the minus 2. We solved it, we calculated it. So they did a mistake, okay? So here, we will get 4.53 times 10 to the power of minus 4. What will we get here? It will be 1.25 times 10 to the power of minus 2 over 2. This would be what? This would be 6.25 times 10 to the power of minus 3. For sure. So, again, they did a mistake, and my limiting reagent in this scenario is what? My limiting reagent is PbNO3 2. Now I need to solve my whole equation based on this. What does this mean? This means I need to use the ratio of PbNO3 2, right? So we finished part D. Now we moved on to part E. Calculate the molar concentration. Oh, okay, we just needed to find the limiting reagent. Now the molar concentration of NO3 minus aqueous left in the mixture after the reaction is complete. Now, do you remember? Our limiting reagent was PbNO3, right? How much was the number of moles here? It was 4.53 times 10 to the power of minus 4, if I'm not mistaken. Yeah. Now back to what I was saying. In where you separate them into their ions, Pb2 plus and NO3 minus. It's not balanced, so you balance it by putting a 2 over here. So now you have 2 positive, 2 negative charge, right? And now How do we find the concentration? It's gonna be what? They told us that the volume does not change, like the initial volume of the solution does not change. So it's what? It's 1.25 milliliters, which is 0.125 liters, right? So now it's going to be 2 times NO3 minus, so 2 times the number of moles, divided by the volume, which will give me a concentration of 2 times 4.53 times 10 to the power of minus 4 over 0.125. This will give me an answer of approximately the concentration to be 7.25 times 10 to the power of minus 3 molarity. That's it for question 21. We'll move on to 22. A sample containing 2.12 gram of Na2CO3 was dissolved in 500 centimeter cubed solution. Calculate the concentration of all the ions present. Okay, so this is a very nice equation. So whenever they say all of the ions present, what do? We separate into the ion Na plus, CO3, 2 minus. It does not balance, so I'll put the 2 here. So now I have 2 positive, 2 negative. They balance each other out. Now, how can I find the concentration of Na2CO3? Mass over molar mass equal number of mole equal concentration times volume. That means mass over molar mass equal concentration times volume. I'm looking for what? For the concentration. That means concentration is equal to mass over molar mass times volume. Okay? So my mass, which is 2.12, over the molar mass of Na2CO3, which is 106, okay, multiplied by the volume, which you change it into meter cubed or decimeter cubed, my bad, or liters, okay, it would be 0.5, okay. So then after solving, it will give you an answer of 0.0400 molarity. Now this is the concentration for Na2CO3. So 1 Na2CO3 gave me 0.04. 2 Na plus will give me 2 times 0.0400, which is 0.0800, okay. And then 1 CO3 2 minus will give me 1 times 0.0400 molarity. So my answer is going to be for the concentration of Na plus at 0.0800 molarity, and for CO3 2 minus at 0.0400 molarity. We'll move on to question number 23. Question 23. A sample containing 25 centimeter cubed of a 0.20 molarity NaCl solution was mixed with 75 centimeter cubed of a 0.020 molarity CaCl2 solution. Calculate the concentration of the Cl- ions present in the solution. Okay, how do we find this? First of all, we need to find the total number of moles of Cl-. After that, you'll divide it by the total volume, and you will get what? You'll get the total concentration of Cl-. Now, personally speaking, we start with NaCl, right? We separate into the ions, Na plus, Cl-. So it's in a ratio of 1 to 1, right? Now, my number of moles is going to be concentration times volume. So it's going to be 0.025 times 0.2, okay? By accident, I deleted my writing. So, where was I? I was 0.025. I changed from centimeter cubed to decimeter cubed. Times 0.20 will give me the number of moles to be 5 times 10 to the power of minus 3. So 1 NaCl gives me 5 times 10 to the power of minus 3, right? That means 1 Na plus will give me 5 times 10 to the power of minus 3, and 1 Cl minus will give me 5 times 10 to the power of minus 3. So first thing we have, Cl minus is what? Is 5 times 10 to the power of minus 3 moles. The first one. Now, the second one, we'll need to find the number of moles of Cl minus and CaCl2. So Ca2 plus, Cl minus, not balanced, so you put a 2 here. So it's in a ratio of 1 to 2, right? So what does this mean? This means it's going to be 0.075 times 0.020. Okay, so this will give me what? This will give me 1.5 times 10 to the power of minus 3 moles. Now, of course, this is not to ratio, okay? So 1 CaCl2 will give me 1.5 times 10 to the minus 3. So 1 Ca2 plus will give me 1.5 times 10 to the power of minus 3. And then 2 will give me 1.5 times 1.5 times 10 to the power of minus 3 times 2. Which is what? Which is 3 times 10 to the power of minus 3. So again, Cl minus 3 times 10 to the power of minus 3 moles. Let's erase this. Now, the total number of moles, we can find it by adding them. So 8 times 10 to the power of minus 3 moles over the total concentration, which is 75 centimeter cubed plus 25 centimeter cubed, so 100 centimeter cubed. In decimeter cubes, that's 0.1. So divided by 0.1, it will give me my answer to be 0.080. And this is what? This is the concentration of Cl minus ions present in the solution. We move on to 24. What does it say in 24? Magnesium reacts with hydrochloric acid according to the chemical equation, blah, blah, blah. A sample of 60 centimeter cubed, 1 molarity HCl is added to a beaker containing 1.2 gram of Mg. Calculate the number of moles of H2 gas produced. So we need to first of all find which of the following is the limiting reagent. Okay, so we can do that by finding the limiting reagent ratio. So we start with the number of moles of Mg. Number of moles of Mg is 1.2 over 24, right? So that's 0.05, 0 moles. And then here, it's 0.060 times 1, which is 0.060. Now what do we do? Of course, this is for HCl, this is for Mg. Now what do we do? Of course, we need to divide by the coefficient. So divide by 1, divide by 2. This is 0.030, 0.050. This is smaller. This is what? This is my limiting reagent ratio. That means what? That means my limiting reagent is HCl. Perfect. Now that means everything moves on how I move with the HCl. So 2 becomes 0.060 moles. How much will 1 H2 become? It will become 0.030 moles. And that's pretty much what they're looking for. The number of moles of H2 gas produced, which is 0.030 moles. Question number 25. A lab technician is asked to prepare 500 centimeter cubed 0.50 molarity H2SO4 solution from a 6 molarity H2SO4 stock. Explain how the technician can do this. Whenever they say prepare, we think of C1V1 equals C2V2. But here there's a very important trick we need to pay attention to. And this is the fact that this is in centimeter cubed. You could keep it because then you get your answer to be the same value but in centimeter cubed, and then you can change it. But it's preferable always to change it to scientific unit. So it will be 0.500 decimeter cube. This is the volume multiplied by the concentration, 0.50, is equal to the volume that we need to find multiplied by the concentration, which is 6. So volume 2 is equal to 0.5 over 0.5, so 0.25. Over what? Over the concentration 6. So what will it be? It will be 0.042 decimeter cubed. Okay, now it's preferable to change it back to centimeter cubed, so 42 centimeter cubed. Why? Because now you can say, using a burette, transfer 42 centimeter cubed of 6 molarity acid into a 500 centimeter cubed volumetric flask, and then add enough water till the bottom of the meniscus is tangent to the etched mark on the neck, and then shake well to homogenize. We'll move on to question number 26. Question number 26. A student mixes a solution of potassium carbonate K2CO3 aqueous with a solution of calcium chloride CaCl2. A calcium carbonate precipitate is formed. Write the balanced equation. When they say precipitate, CaCO3, right? That means this is what this is, a solid. Now, what reacts to form CaCO3? For sure, it's the Ca2 plus aqueous and the CO32 minus aqueous. So Ca2 plus aqueous plus CO32 minus aqueous is gonna give me CaCO3 solid. We'll move on to part B. What does it say in part B? It says The diagram below shows a particulate representation of the solution after the reaction stops. However, the diagram is incomplete. Knowing that K2CO3 solution is in excess, that means which is in limiting, that means the what is this? CaCl2? Yeah, the CaCl2 aqueous is what is delimiting, okay? They said what they said, draw any species that are missing. Okay, perfect. So what is the equation? The equation is CaCl2 aqueous plus K2CO3 aqueous will give me CaCO3 solid. Now we know that K2CO3 is in excess. That means we're going to have CO3 minus in excess, and the Ca2 plus is the limiting. That means it will be fully consumed. We're not going to see it anywhere, right? However, what we will have left is 2Cl minus, right? Because if you do the Ca2 plus and then you do the balance, it will be 2Cl minus. And in the diagram, we only have one Cl minus. So what we need to add is one more Cl minus. Or basically, it's not only that you have 2Cl minus, it's basically you double the number of moles of Cl minus. So if I have one circle, okay, I will double it. So then I will have how much? I will have 2 circles now. Same exact thing for K2CO3, by the way. If you do it, you will have CO3 2 minus, okay, and 2K plus after balancing, right? CO3 2 minus, I have only one CO3 2 minus, so it's going to be 1 times CO3 2 minus, right? So I'm only going to have one CO3 2 minus. But now, it's going to be 2K plus. How many K plus do I have originally? I originally have 2K plus. That means I will multiply the number of moles of K plus I had, which is how much? Which is 2 in the scenario, by 2. That means I'm going to need to double it. So when I double it, I will have now 4. So this is what my solution is supposed to look like. I'm supposed to have 4K plus, 2Cl minus, and 1 CO3 2 minus. We'll move on to question number 27. Hydrogen peroxide, H2O, decomposes to produce water and oxygen gas. A particulate representation of hydrogen gas is shown below. Write the equation of decomposition reaction that occurs. So 2H2O2, right? This is a liquid. It decomposes to give me 2H2O liquid, right? In addition to O2 gas. Draw in the empty box the particulate representation of all molecules left at the end of the reaction. So first of all, we look at the initial, which is the H2O2. How many do we have? How many moles of H2O2 do we have? We have 4 moles of H2O2. Oh my goodness, 4 moles of H2O2. So that means 2 became what became 4. That means 2 will also become 4, and 1 will become what? It will become 2. That means in the product, I'm supposed to have 4 water molecules and 2 oxygen molecules. So I'm going to make the water molecules. Actually, let me do it like this. I'm going to make hydrogen red and oxygen blue. So my water molecule will be like this. A big blue, 2 small red. And I have to repeat that 4 times. So it's time to draw. So this is the 4 moles of water. And what do I have left? I have the O2 gas, right? So I'm going to have 2 moles of O2 gas. So 1 and then 2. So this is what my figure is supposed to look like. We move on to question number 28. Consider the reaction N2 gas plus 3H2 gas gives us 2NH3 gas. If we mix 5 moles of N2 with 9 moles of H2, then the diagram that shows the mixture after the reaction. Okay, so look basically what they gave us. They gave us the reaction. We need to find the limiting reagent ratio based on the moles they gave us. They said 5 moles of N2, so 5 divided by the coefficient, which is 1. This is for N2. Then 9 moles of H2, 9 divided by the coefficient, which is 3 of H2. Now from these two, we can find the limiting reagent. This has a ratio of 5, this has a ratio of 3, this is smaller, H2 is my limiting reagent. That means the whole equation revolves around H2. I like to take it like this. So if 3 became 9, how much is 1 supposed to become? It's supposed to become 3, and 2 is supposed to become 6, right? So if I had initially 5 moles of N2, and I only used 3 because I'm supposed to like use 3, 5 moles of N2, and I only used 3, I'll be left with 2 moles of N2. So in my solution, I'm supposed to have 2 moles of N2 in my product, okay? And what did I form in my product? I formed 6 moles of NH3 gas. Now, to compare the sizes, for sure H2 has a smaller atomic radius than N2, so that's why you choose the ones with the big circles, not the small ones. The small circles, they are representation of H2, and we don't have any H2. Instead, we have, okay, this you also don't choose it. You're left with this one. Why? Because it has 2 N2, right? And it has how much? It has 6 NH3. Perfect. We'll move on to question number 29. What volume of 0.50 molarity HCl is needed to neutralize exactly 20 centimeter cubed of a 0.020 molarity CaOH2 solution? So what you need to know is that the number of moles of H plus should be equal to the number of moles of OH minus, right? In order for there to be what? In order for there to be neutralization. Okay? So here, the number of moles of my H plus is what? It's gonna be, first of all, you draw the ratio. It's 1 to 1. So it's gonna be the concentration, 0.5, times the volume, which we need to find, okay, is equal to, now the number of moles of OH minus. Here, if I drew the ratio, Ca2 plus, OH minus, not balanced to OH minus, so 1 to 2. So now we don't forget, because we're dealing with OH minus, to multiply by 2. So 2 times the volume, which is 20 centimeter cubed, times the concentration, which is 0.020, right? And so then volume is equal to 2 times 20 times 0.020 over 0.5 will give me my answer to be 1.6 centimeter cubed. That's it for 29. We move on to 30. What volume in milliliters of a 0.10 molarity potassium permanganate solution, okay, is needed to completely oxidize? So what does this mean? This means the number of moles, or let's not say the number of moles, the ratio, more preferable, of KMNO3, which if you look in the reactants is MnO4 minus. So the ratio of MnO4 minus, okay, should be equal to what? Should be equal to the ratio of copper nitrate. So they're only dealing with copper, should be equal to the ratio of copper. What does this mean? This means the number of moles of MnO4 minus over 1 is equal to the number of moles of Cu plus over 5. Why? Because number of moles over the coefficient. Now, anyways, what are they looking for? They are looking for the volume of the potassium permanganate, right? So it should be N is equal to Cv, right? So it should be C times V here, and it should be C times V here. So what's my concentration? It's 0.10 times the volume over 1, MnO4 minus, is equal to what? Is equal to the concentration of Cu plus, which is 0.30, times the volume, which is 10 milliliters, over what? Over 5. Now you just need to do cross multiplication to solve. So you will get what you will get. You will get your answer to be what? To be, my volume V is going to be equal to what? It's going to be equal to 6.0 milliliters. Don't forget to choose it to the correct significant figures. 33, 34, 35, 36. Okay, I'm not gonna be doing the top questions. The top questions are easy to do for yourselves. So I'm gonna finish at 36. That means I have 31 till 36 left. Okay, perfect. So a student prepares 250 milliliters. This is volume of a standard solution using the mass 5.11 grams of potassium hydrogen. In order to use it to determine the concentration of an NaOH aqueous solution, KHP is a monoprotic acid, right? And the molar mass of KHP is 204.22 grams per mole. And what happens? It will react with NaOH in a 1-to-1 ratio. So what did the student do? He followed the procedure to perform the titration, right? So what are they asking us? They're asking us for the volume. Actually, no, in part A, they're asking us calculate the concentration of the standardized KHP aqueous solution. So what do I have? I have my volume, I have my molar mass, I have my mass. We can easily calculate the concentration. Mass over molar mass equal number of moles. Number of moles is equal to concentration times volume. That means this is equal to this. I need concentration. That means mass over molar mass times volume is equal to concentration. Don't forget to change volume to the SI units. So 5.11 over 204.22 times 250 times 10 to the power of minus 3. And this would give me an approximate answer of 0.100 molarity. So this is the concentration found in part A. In part B, they said fill in the table with the missing volumes. How do we find that? You need to subtract, and you need to do it based off the correct significant figures, which is 2 decimal places, okay? So here it's gonna be 28.10 when you subtract the final minus initial, 25.6, 0.60, 25.95, and 25.50, and 25.50. Now in part C, what are they doing? They said calculate the average volume of KHP solution needed. You don't take the ones that are far off, you take the closest possible values, which are 25.50 plus 25.50 plus 25.60 divided by how many do you have? You have 3, right? So 25.50 plus 25.50 plus 25.60 over 3 will give me an answer of what? Will give me an answer of 25.53 milliliters. So this is the average volume. Part D, use the average volume of KHP needed to calculate the concentration of the NaOH solution. Now what's important is, if we read in the beginning, they told us it's a ratio of 1-to-1. So that means C1V1 is equal to C2V2. If they told us a ratio of 1-to-2, it would be C1V1 equals C2V2 times 2, for example. So the ratio is very important. It will help us determine what's the equation to use. So C1V1 equal C2V2. So it's concentration of KHP. We found it to be 0.100 times the volume of KHP, which we found to be 25.53, is equal to concentration 2, which we need to find, okay, times volume 2. What's volume 2? I think they mentioned it somewhere up that volume 2 is 25 milliliters. So you can move this to the other side, and now you will get the value of concentration 2. So it's 0.100 times 25.53 over 25. I'll get my answer C2 to be 0.102 molarity. Part E, if the solid KHP used to prepare the standard KHP solution was initially wet, how does that affect the calculated molar concentration of NaOH? So if KHP was initially wet, its mass that we calculated would not be the actual mass, it would be its mass plus water, right? So we'd get the wrong number of moles. If we got the wrong number of moles, then like our whole like equation and solving would be considered incorrect, okay? Okay. Question number 32. 25 centimeter cubed of 0.160 NaOH solution is needed to neutralize solution containing 0.146 gram of a monoprotic acid. Calculate the molar mass of the acid used. So when they say a monoprotic acid, that means it has one hydrogen, right? So one hydrogen here, one OH here, right? So what does this mean? This means it's in a ratio of 1-to-1. If it's in a ratio of 1-to-1, then what can we say? We can say that the number of moles of H plus is equal to the number of moles of OH minus, right? So 25 times, change it to decimeter cube, don't forget. 25 divided by 1000 times 0.16 is equal to the mass over the molar mass M. So what does this mean? This means the molar mass is the mass, 0.146, divided by 25 over 1,000 times 0.16, right? So that means 0.146 over 25 divided by 1,000 times 0.16. This would give me my answer to be 36.5 grams per mole. Don't forget grams per mole. We'll move on to question 33. A tablet contains magnesium bromide, MgBr2, and glucose. To determine the percentage of magnesium bromide in the tablet, the following procedure is used. Weigh the tablet, crush it and dissolve it in blah blah blah. Okay, procedure. What do they want in part A? Use the equation and the data below to calculate the mass percent of magnesium bromide in the tablet. Okay, so what did they tell us? They told us in the table that the mass of precipitate and filter paper after drying is what? Is 1.874 grams, right? So 1.874 grams. We subtract it from the mass of the dry filter paper, which is 1.236, right? So after subtraction, you will get the answer to be 0.638 grams, right? Now this is the mass of what? This is the mass of PbBr2 solid. How do we find the number of moles? 0.638, which is the mass, divided by the molar mass, which is 367, will give me my answer to be 1.74 times 10 to the power of minus 3 mole. Now, from what I'm understanding is that PbBr2 will have the same number of moles of MgBr2. So now that we found the number of moles of PbBr2, which is 1.74 times 10 to the power of minus 3, right? We can find the number of moles of MgBr2, which is also 1.74 times 10 to the power of minus 3, and we can find the mass times. So you do number of moles times the molar mass to get the mass. So put it on the calculator, you will get 0.320 grams. Perfect. Now, you will take this mass, 0.320 grams, divided by the mass of the tablet, 0.568 grams, and you will multiply by 100, and you will get your percentage to be 56.3%. Part B. The percentage calculated is larger than the actual percentage. What mistake might have happened? Okay, so they only heated it once, right? They didn't heat it multiple times. So in order to prevent any mistakes, what should have happened is that they should have heated it multiple times until it leads to a constant mass. Heating once left some water in the precipitate, which is recorded as a larger mass than the actual mass, and led to a greater mass percent. So if you heat it multiple times until it reaches a constant mass, you will be ensured that this is the mass of only this and not of water. Which ions are present in the highest concentration in the filtrate? So the most present would be the spectator ions. So if you go back up, you see that it was PbNO3 that acts, yeah? It acts with what? It acts with... Okay, my bad, actually, look. This is PbNO3 will react with MgBr2 to produce for me PbBr2. So this is why PbBr2 and MgBr2 have the same number of moles, because they're in a ratio of 1 to 1. Okay? Now what are the ions that react? Pb reacts, Br2 reacts to form PbBr2, and now we're left with Mg and NO3. Now, if you did it initially, it would be Pb2 plus and NO3 minus, not balanced, so you'll put a 2 here. If you did this here, it's Mg2 plus and Br minus, not balanced, so you'll put a 2 over here. But we're comparing Mg2 plus and 2 NO3 minus. It's in a ratio of 2 to 1. That means for sure, which will be the higher concentration, it would be the NO3 minus, because even though it's a spectator ion, as well as Mg2 plus, it still has a greater concentration. Okay, we'll move on to 34. A solution is formed by mixing 1 liter 1 molarity KCl with 1 liter 1 molarity PbNO3. Okay, so let us write the reaction. PbNO3 to react with KCl to give me what? To give me PbCl2 in addition to K plus and NO3 minus. Now, of course, this is not balanced, so you'll put a 2 over here. Why? Because we have Cl2 and we need it to be 2. That means we have 2K plus and 2NO3 minus. Okay, so they said what? They said complete precipitation. Now, anyways, let us find the number of moles of this and the number of moles of this. It's 1 times 1, which is 1, and 1 times 1, which is 1. Let us see which one is the limiting reagent by taking each one and dividing by the coefficient. So 1 over 1 is 1. So this has a ratio of 1. And then 1 over 2 is half, which is smaller than 1. This has a ratio of half. So for sure, my limiting reagent is what? My limiting reagent is 2KCl. So how do I calculate the mass of PbCl2 that will form? Well, very simply, it's going to be what? It's going to be the number of moles of PbCl2, right? What is this? PbCl2 divided by the coefficient, which is 1, is equal to the number of moles of the limiting reagent, which is KCl, divided by the coefficient, which is what? Which is 2. So we already find the number of moles of KCl, 1, okay, 1 over 2. What does this mean? This means that the number of moles of PbCl2 is half, okay? Right? Or we could say that 2 gave me 1, so 2 moles became 1 mole. How much will 1 mole become? It will become half a mole. So now what can we say? We can say that the mass of PbCl2 formed is half times... Oh, actually, I believe they want the mass... Yeah, the mass of PbCl2 formed. So it's going to be half multiplied by the molar mass of PbCl2, which is how much? Which is 278. So you should get your answer to be 139. To two significant figures, 1.4 times 10 to the power of 2 grams. Okay, very, very, very important. Now they want the molar concentration of all ions left in the solution. Now, which one do I not have left? I don't have Cl left. Why? Because KCl is my limiting reactant, right? It's my limiting reagent. And which of these actually reacted? Cl actually reacted. K is just a spectator ion, so K remains. K stays. But Cl, being my reagent, is what is gonna disappear completely because it's my limiting reagent. Now, they want the molar concentration. How do we find the molar concentration? It's number of moles over the volume, right? So the molar concentration of K plus, it's gonna be what? It's gonna be the number of moles, because it's in a 1-to-1 ratio, the number of moles is gonna be 1, over the volume, which is 1 liter plus 1 liter, which is 2, so it's gonna be 0.50 molarity. For NO3 minus, it's in a 1-to-2 ratio. That means it's gonna be 2 because the number of moles of PbNO3 was 1. So it's gonna be 2 times 1, which is 2, over the total volume, which is 2. So it will give me what? It will give me 1.0 molarity. For Cl minus, it's 0 because it's completely used up, okay? Now, the number of moles of Pb2 plus left, this is very, very, very important. First of all, I see. What was my limiting reagent ratio? It was 1 over 2, right? So I will take the number of moles of my Pb, right? So PbNO3 it's what? Number of moles being 1, and this is 1. So 1 PbNO3 gives me 1. So 1 Pb2 plus will give me 1, right? So it's going to be my number of moles, 1, minus the ratio, which is 0.5 of the limiting reagent, which will give me what? Which will give me 0.50 moles. Now this is the only thing left, divided by the total volume, which is 2, will give me concentration of 0.25 molarity. We'll move on to question 35. So what do they want in this question? Iron 3 ions react with whatever to form dichloride blah blah blah. Excess is added to a 50 milliliter sample of this. Use the plot below to find the mass of iron chloride used to make the 50 milliliter sample, knowing that the absorbance of the solution is 0.60. So if the absorbance is 0.60, I will come here and I will use this value, which is 1.2 times 10 to the power of minus 3. You should know how to change and read the graph. Okay, this is very important. So it's 1.2 times 10 to the power of minus 3. What? This is the concentration, right? Now, what do they want? They want the mass of iron. Mass over molar mass is equal to what? Is equal to the number of moles. So mass is equal to number of moles times molar mass. We also know number of moles is concentration times volume. So we can put this here. So now my mass is going to be my concentration, which is 50 times 10 to the power of minus 3 liters, okay, times my concentration, which is 1.2 times 10 to the power of minus 3, times the molar mass of FeCl3, which is 162.2. Put it on the calculator, you will get 9.7 times 10 to the power of minus 3 grams. We'll move on to question 36. To determine the optimum wavelength that must be used in an experiment that measures the concentration of a colored species, a sample of the solution is measured and used to determine the amount of light it absorbs over a range of wavelengths, blah blah blah. According to the plot, what's the optimum wavelength for the experiment? You just take the highest point of absorbance, and you see that the wavelength is 471. That's it for this video. Thank you guys for watching. I hope you enjoyed and have a wonderful day. I'm not gonna do the top questions. You guys should do them by yourselves, okay?